Hello all, again welcome back to Tungal online classes. Now we are discussing magnetism and matter chapter. In the previous class we have seen that the bar magnet is equivalent to current carrying solenoid. That concept we have seen. Now in this session we will see what are the comparison between electrostatics and magnetism, and when a bar magnet placed in a uniform magnetic field, how it experiences torque. That we will see in detail. Now it's time to move. Let us go. What is the comparison between electrostatics and magnetism? Let us say that. Comparison between electrostatics and magnetism. Comparison between electrostatics and magnetism. Okay. So let us take two columns. In one column we will take electrostatics. In second column we will take magnetism. See here. In one column we will take electrostatics. In second column we will take magnetism. Here very simple, you can make the difference between or comparison between electrostatics and magnetism in detail. See here. In electrostatic basically we are represent the charge. So in electrostatic, shall I take the first one? So in electrostatic simply you can call the charge, that is represented by quantity small q, right? But in the magnetism, how the charge can be replaced? In the magnetism, the charge can be replaced by pole strength. In magnetism, in place of the charge, how to say? In place of the charge in magnetism, we are taking pole strength. Pole strength represented by small m, right? In electrostatics, electric field is present. See here. In electrostatics, electric field is there. Electric field represented by quantity capital E. But in magnetism, electric field is replaced by magnetic field. See here. Here what quantity is there? Magnetic field is there. Magnetic field simply represented by quantity capital B. Right? In electrostatics, there is a proportionality constant that we are calling Coulomb's constant. What is Coulomb's constant in electrostatics? See here. Coulomb's constant equal to what value? K. K is equal to what value? 1 divided by 4 pi epsilon naught. Right? Similarly, in the magnetism, there is proportionality constant. Here proportionality constant also represented by K, but its value is equal to what value? That is K is equal to mu naught by 4 pi. Right? In electrostatics, we can define electric dipole moment. How to define electric dipole moment? The product of either charges and distance between two charges. See here. Here how to take electric dipole moment? Electric dipole moment is equal to P. What is P? P is equal to what value? Q into 2L. Right? Similarly, in the magnetism, how to replace magnetic dipole moment? See here. In this case, magnetic dipole moment is equal to capital M. So Q can be replaced by what value? Small m, that is pole strength. M into how much? M into 2L. Right around this. In electrostatics, dipole moment can be represented by this formula. In magnetism, dipole moment, magnetic dipole moment can be represented by this formula. See here. Similarly, in electrostatics, I can define electric field intensity. How to define electric field intensity? Or electric field intensity is equal to what value? Force experience per unit positive charge. Force experience per unit positive charge. Or how to represent force? Force is equal to what value? That is Q into E. Force is equal to Q into E. Similarly, in the magnetism, how to take? See here. In this magnetism, I can take directly. Look at me. M is equal to what value? Small m into what value? 2L. In magnetism, how to take? Magnetic field can be defined as magnetic force experienced per unit pole strength. Write on this. Now, how much magnetic force is acting? F is equal to what value? Small m into B. Write on this. Similarly, in electrostatics, when a dipole placed in a uniform magnetic field, it experiences torque. How the torque can be represented in electrostatics? Torque is equal to what value? That is P cross E. Right? Then in magnetism, how to represent the torque? Whenever a bar magnet or a magnetic needle or a magnetic dipole placed in a uniform magnetic field, it experiences torque. So in torque, P can be replaced by what value? P can be replaced by capital M. Capital M. E can be replaced by what value? Capital B. This we can take. Similarly, you can make so many comparisons. Comparison between electrostatics and magnetism. In simple manner, you can take, in electrostatics, electric field is there, but in magnetism, magnetic field is there. In electrostatics, charge is present. In magnetism, pole strength is present. Right? So, like this, so many comparisons we can make. Now, our point is, when a bar magnet placed in a uniform magnetic field, it experiences torque. How much experience torque? Tau is equal to M cross B. That concept we will see. When a bar magnetic placed in a uniform magnetic field, and when a magnetic needle placed in a uniform magnetic field, that experience torque. Before that, remember that in electrostatic, this much force is acting. In magnetism, how much force is acting? This much force is acting. Remember this. So by taking this concept, we will go how torque is experienced by bar magnet when it is placed in a uniform magnetic field. That we will see. See here, concept is torque experienced by bar magnet in a uniform magnetic field. Torque experience by bar magnet in uniform magnetic field. In uniform magnetic field. Right thing. So let us see this concept. How a bar magnet placed in a uniform magnetic field, it experiences torque. Before that, students, let us take a bar magnet. Already we know that rectangular shape cross section of the object which having north pole and south pole, when it is freely suspended, it aligns in north south direction. That we are calling bar magnet. See here how the bar magnet is there. Now I would like to take a bar magnet. Consider it is a bar magnet. This is a bar magnet, right? This is a bar magnet. So it consists of south pole, right? This we are calling south pole, and the second called the north pole. Right or wrong? The imaginary line joining from north pole to south pole, this we are calling magnetic length. How much this magnetic length? This magnetic length can be represented by 2L, right? And this bar magnet has a pole strength, equal and opposite pole strength. So here, this much pole strength represented by small m. This also represented by small m, right? Now, when this bar magnet placed in a uniform magnetic field, let us take uniform magnetic field. In the previous class, already we have seen that the magnetic field whose magnitude and direction must be same at every point, that we are calling uniform magnetic field, right? Uniform magnetic field can be represented as set of parallel lines. How we will take? So let us take, these are nothing but uniform magnetic field lines. This is uniform magnetic field lines. Right? This is uniform magnetic field. So the magnitude and direction must be same at every point. This can be represented by set of parallel lines. This I can call uniform magnetic field. Right, students? When uniform magnetic field is there, for this bar magnet there is magnetic dipole moment. From where to where? Magnetic dipole moment from south pole to north pole. How to take? This magnetic dipole moment direction can be taken from north pole to south pole to north pole. Right around this. Now, in presence of this bar magnet, in presence of this magnetic field, this north pole experience magnetic force. How to take the magnetic force? Magnetic force is equal to what value? Magnetic force is equal to product of pole strength into magnetic field. This again called magnetic force. So here already one property is there. Magnetic field lines can travels from north pole to south pole. This magnetic field lines can travels from north pole to south pole. Here north pole is there. Here south pole is present. So that north and south are attract each other. In presence of this magnetic field, this north pole experience along the direction of magnetic field. That force can be given F is equal to M into B. Right around. Similarly, somewhere north pole is present because magnetic field lines travels from north pole to south pole. Right around. In presence of this magnetic field, this south pole experience magnetic force. How much magnetic force? F is equal to again what value? This is M into B. Right? Because south and north are attract each other. So in presence of magnetic field, the north pole and south pole experience equal and opposite forces. They experience equal and opposite forces. So here north pole experience this much forces along the direction of magnetic field. South pole experience opposite to direction of magnetic field. Here equal and opposite force are there. Wherever equal and opposite force are acting, we can say on that body torque is acting. How to define the torque? The torque is nothing but the product of either force and perpendicular distance between two forces. Here in this case, how to take the perpendicular distance between two forces? See here, this force acting in this direction and this force is acting in this direction. What is the perpendicular distance between two forces? I can take, this is the perpendicular distance. Are you following this? This I can call perpendicular distance. So let us take this value is equal to Z. What is angle between magnetic field and magnetic dipole moment? This angle I can take. This angle can be represented by theta. Are you following this? So that here equal and opposite force are acting, and this we can call perpendicular distance between two forces. Remember. So I can call this nothing but south pole. Right? So this I can call the north pole. Right around. Equal and opposite force are acting. Wherever equal and opposite force are acting, I can define torque. How to define torque? The product of either force and perpendicular distance. See here perpendicular distance between this force and this force can be represented by Zn quantity. Here how to define torque? The torque can be defined as a tau is equal to product of either force and perpendicular distance between two forces. Right? So shall I call it as equation number 1? I can call this equation number 1. But here, how much magnetic force? Force F is equal to M into B, or force is equal to F is equal to M into B. Then I need Zn. Look at this triangle. I can call SNZ looks like a triangle. Which is the triangle? Triangle SNZ looks like triangle. So in this triangle, I can take sine theta. What is sine theta? Sine theta is equal to opposite by hypotenuse. See here. What is sine theta? Sine theta is equal to opposite. Opposite is equal to what value? Zn. What is hypotenuse? Hypotenuse is equal to what value? Sn. Right? Again you can take sine theta. What is sine theta? Sine theta is equal to what value? Zn. Zn keep it up same. What is Sn? Sn is equal to distance between north pole and south pole. That is represented by what value? 2L. Right? Again from this Zn, what is Zn? Z into N is equal to what value? 2L sine theta. Let us call it as equation number 2. Right? Then come to equation number 1. Tau is equal to torque. Torque is equal to force into perpendicular distance. What is force? Force is equal to M into B. Look at me here. Torque is equal to what value? Force. Force is equal to M into B. Product of pole strength and magnetic field. What is Zn? Zn is equal to what value? Zn is equal to 2L sine theta. 2L sine theta. But we know that magnetic dipole moment. How to define magnetic dipole moment? the product of either pole strength and distance between two poles, that is small m into 2l is equal to capital M. Then how to take? Torque is equal to what value? Torque is equal to m into b sin theta. M into b sin theta. In vector form, how to represent? In vector form, tau is equal to what value? Tau is equal to m cross b. Tau is equal to m cross b. So that when a bar magnet placed in an uniform magnetic field, it experiences torque. Due to this torque, this bar magnet try to rotate along the direction of magnetic field. How it rotate? Actually, this is south pole, this is north pole. How this rotate? This bar magnet is like this. In presence of this torque, this dipole or this bar magnet try to rotate in this direction. I mean, it tried to rotate along the direction of magnetic field. How it rotate actually? I can call this is south pole and this is north pole. So this will try to rotate in this direction. Try to rotate. So that due to torque, the dipole or the bar magnet try to rotate along the direction of magnetic field. Then question is, when torque is maximum on the bar magnet, when torque is minimum on the bar magnet? That we'll see. See here, very simple. Torque is equal to mb sin theta. Torque experienced by the dipole depends on strength of magnetic dipole moment, depend on strength of magnetic field, and also depends on angle between magnetic dipole moment and direction of magnetic field. We can call this the direction of magnetic field. This is nothing but direction of magnetic dipole moment. Right around this. Then let us see here. So now I will take a situation like this. In what cases or on what cases on the bar magnet the maximum torque is experienced? Let us see that. See here. Now initially I can take this is nothing but a uniform magnetic field. Right or wrong? This is nothing but a uniform magnetic field. In this uniform magnetic field, I want to place the bar magnet in this situation. Like this situation. So I can call this nothing but south pole or can call this nothing but the north pole. This is the distance between north pole and south pole. Right or wrong? How to take the direction of magnetic dipole moment? Direction of magnetic dipole moment can be taken from south pole to north pole. I can take this quantity is capital M. Right or wrong? This quantity I can take the capital M. Now in between this magnetic dipole moment and magnetic field, how much angle available? Theta equal to 90 degree available. I mean, when a bar magnet is placed perpendicular to direction of magnetic field, theta equal to what value? 90 here. Theta is equal to 90. Wherever sin 90, that is when. Sin 90 when mean how the torque can be experienced. Torque is equal to what value? M into B. Maximum torque is experienced. When maximum torque is experienced? When a bar magnet placed perpendicular to direction of magnetic field, it experiences maximum torque. Then I will take second situation where torque is zero. No matter how much strength of magnetic field or how much strength of magnetic dipole moment, in that case no torque is experienced. That case we will see. See here. Now again I will take uniform magnetic field lines. This is nothing but uniform magnetic field lines. Right or wrong? So now I would like to take a bar magnet. Shall I take this is a bar magnet? This is the bar magnet. Right or wrong? So I can take this nothing but north pole or I can take this nothing but south pole. Right or wrong? This is the line joining from north pole to south pole. Right? What is the direction of magnetic field? This is the direction of magnetic field. What is direction of dipole moment? This is nothing but direction of dipole moment. Right? Now I can take one more situation I can take. In this case, angle between magnetic dipole moment and magnetic field. How much angle available? Theta equal to 180 available. Or one more situation I can take. See here. Again I will take this nothing but uniform magnetic field lines. Right or wrong? This is nothing but uniform magnetic field lines represented by quantity what value? B. Now in this uniform magnetic field again we will take a dipole or bar magnet. This is the bar magnet. So I can call this nothing but south pole, and what about this? This is the north pole. The imaginary line joining from north pole to south pole. This we are calling nothing but magnetic dipole length. Then in this case magnetic dipole moment from where to where? From south pole to north pole. Right? In this case angle between magnetic dipole moment and magnetic field. How much angle available? 0 degree available. Now see here, come to this point. Either bar magnetic placed parallel to direction of magnetic field or anti-parallel to direction of magnetic field, where theta is 0 or theta is 180. Theta 0, sin 0, 0, sin 180, 0. In both cases, both cases, what is torque? Torque is equal to what value? 0. Because sin 0, 0, 0 into m is 0, torque is equal to 0. Or sin 180 is 0, 0 into m is 0, then torque is equal to 0. I mean, when a bar magnet, its dipole moment parallel to direction of magnetic field or anti-parallel to direction of magnetic field, there no torque is experienced by the bar magnet. So this is the case how torque experienced by bar magnet in an uniform magnetic field. Now instead of bar magnet, we will take a magnetic needle, that magnetic needle placed in a uniform magnetic field. There how it happens, that case we will see. Our next concept is magnetic needle in a uniform magnetic field. See here. Okay students, now let us take, now I will take a bar magnet, now I will take a uniform magnetic field. In that uniform magnetic field, let us take a magnetic needle placed in it. See here, concept is magnetic needle in uniform magnetic field. Right, magnetic needle in uniform magnetic field. This concept we will see, students. Now I would like to take a magnetic needle, the magnetic needle placed in a uniform magnetic field. Shall I take? See here. Now simply I will take this, nothing but a magnetic needle. This second type magnetic needle. This magnetic needle consists of south pole, again it consists of north pole, right or wrong. The imaginary line joining from north pole to south pole, this we are calling magnetic length, right. So for this case, what is dipole moment? Dipole moment from south pole to north pole, this we are taking dipole moment, right. Now this magnetic needle placed in a uniform magnetic field. Now shall I take set of parallel lines? Look at me. Again take this, nothing but set of parallel lines. Are you following this? This nothing but set of parallel lines. So this we are calling uniform magnetic field lines. This second call uniform magnetic field lines, right. Now I can call angle between dipole moment and magnetic field. This nothing but direction of magnetic field. Direction of magnetic field, angle between dipole moment and magnetic field represented by what value? Theta, right or wrong? In presence of this magnetic field B, this north pole experience force, how much force? F is equal to what value? Small m into B, right or wrong? Due to this magnetic field, this south pole experience magnetic force, how much again? F is equal to what value? This is m into B. Already we have seen in the previous concept, if equal and opposite force are acting, it experiences torque, right. How much a torque is experienced by this magnetic needle? Due to this magnetic needle, torque is equal to what value? Torque is equal to m cross b sin theta, m cross b sin theta, right or wrong? Due to this torque, this magnetic needle try to rotate along the direction of magnetic field. Due to this torque, how the magnetic needle can oscillate? See here, whenever torque is acting on the magnetic needle, this magnetic needle try to rotate like this. It tried to oscillate like this, like this. Due to this needle, due to this torque, this needle try to rotate like this. Are you following? because due to torque the body try to able to rotate. Due to that rotation this magnetic needle try to oscillate in magnetic field. How it oscillate, that we'll see in detail. Look at me. When your torque is acting on the magnetic needle, that torque tau is equal to m cross b sin theta, and this torque we are calling restoring torque. What we are calling is this we are calling restoring torque. This restoring torque this needle try to rotate with a small angle. I mean the oscillation must be with a very very small angle. If oscillation is very very small angle, then I can represent this is equal to, if theta is very very smaller, then sin theta nearly equal to theta. Why I am taking sin theta nearly equal to theta? Due to this restoring torque, this magnetic needle try to rotate with a very very small angle. If theta is very very smaller, then sin theta nearly equal to theta. Now I can call this nothing but equation number 1. But question arises, how this needle try to rotate in this magnetic field. See here, when magnetic needle from this position, due to this torque, this needle try to comes like this, again goes, try to comes like this, again goes like this. It oscillate in magnetic field. It oscillate in magnetic field, right? Due to oscillation, it make with a small angular acceleration. If this needle has a moment of inertia I and it has angular acceleration alpha, then one more relation is there for the torque. Already we have learned in the first step in rotational system of particles and rotational motion. If the particle has moment of inertia and it has angular acceleration alpha, that tau is equal to what value? Tau is equal to I into alpha, right? What is I? Moment of inertia of the magnetic needle. And what is alpha? Angular acceleration, because it oscillate like this. How it oscillate? It oscillate like this. This is oscillation, it make an angular acceleration alpha, right? Now I can call this is nothing but equation number 2. Actually this we are calling restoring torque, and this we are calling torque experienced due to moment of inertia and due to angular acceleration alpha. Now you can compare just equation 1 and equation 2. What will get? Here also alpha, here also alpha. Sorry, here also torque, here also torque. Then how to represent? Look at me. I can take that mb theta is equal to what value? I into alpha. Right along. Or from this, what is alpha again? Alpha is equal to what value? mb into theta divided by what value? That is I. So let us call it is nothing but equation number 3. Are you following? Already we said that due to this torque, this magnetic needle tried to rotate along the direction of magnetic field. Due to that torque, it oscillate in this magnetic field. It oscillate in magnetic field with the periodic motion. How it rotate actually? This rotate like this. Rotate like this. Like this it rotate. So this we are calling periodic motion. For periodic motion, anybody has a periodic motion, its time period can be given. In what way? Anybody has the periodic motion, time period can be given. T is equal to what value? 2 phi under root of what value? Angular displacement divided by angular acceleration, right? T is equal to 2 phi under root of theta by what is theta? Angular displacement. What is alpha? Angular acceleration, right? Then from equation 3 already we got alpha is equal to mb theta divided by I. Then what is T? T is equal to 2 phi under root of theta, keep it up same. What is alpha? Alpha is equal to what value? mb into theta divided by I goes upside, right? Then theta get cancelled. What is remaining then? T is equal to what value? 2 phi under root of what value? I divided by how much? That is mb. I mean, when a magnetic needle placed in an uniform magnetic field, it oscillates with the time period. The time period T is equal to 2 phi under root of I divided by m into b. Then how to take the frequency? Number of oscillations per unit second, that we are calling number of oscillation per unit second, that we are calling frequency. Simply the reciprocal of time period. Reciprocal of time period I can call frequency. Right along. Reciprocal mean how to represent the frequency? Frequency is equal to what value? 1 divided by 2 phi under root of how much? Under root of mb divided by what value? That is I. Right along. This is the frequency of the oscillation of the magnetic needle in an uniform magnetic field. Right thing. Then how much magnetic field required to oscillate the magnetic needle in uniform magnetic field? From this equation you can calculate how much magnetic field is required to oscillate the magnetic needle in uniform magnetic field. That we will see. See here. Simply this equation T is equal to 2 pi under root of I divided by MB. Square this equation on both sides. What we will get? Square mean. So T becomes T square. 2 pi square. What value? 4 pi square under root of I by MB. I divided by how much? M into B. Right? Or what is B value? B is equal to how much? 4 pi square I whole divided by M into B into how much? That is T square. This much magnetic field required to oscillate the magnetic needle in uniform magnetic field. Right? I mean, when a magnetic needle of moment of inertia I of magnetic moment M placed in a uniform magnetic field, it oscillates with the time period T, it oscillates with frequency F, and it required this much magnetic field to oscillate in uniform magnetic field. Later on this, what is potential energy of magnetic needle when it placed in a uniform magnetic field? That concept we will see in the next class. Thank you, students.